Welcome back, everybody. Final segment for today. And we're going to look at the screen over here. I took this from the book. And we're going to look at what atoms have to do to make bonds. In fact, we'll even go a little out of order from the book here. We'll start on the bottom. Let's talk about atoms. Atoms, especially carbon, in the second row, have the 2s orbital available at the valence level, and they have the 2p orbitals available at the valence level. Remember, valence is the highest energy level that an atom has. And that's what we use for bonding and for putting lone pairs in. So carbon's in the second row. It has a 2s orbital with a spherical shape. And the p orbitals, they occupy individual spaces where they don't touch each other, but they're not spherical. They have dumbbell shapes. You don't have to worry that there's a dark part and a light part. It's symmetrical, and it looks like a dumbbell. Py orbital points in the y direction. The px orbital in the x direction. If you put these on top of each other, they don't touch each other. And the pz is along the z-axis, and it comes straight out and goes back. One thing to note is that the p orbitals cannot be used for making the first bond between atoms, because we want to spread things out as far apart as possible. Why do we want to spread atoms out as far as possible? Because valence shell electron pairs repel each other. That's a great theory name, the Weisseper theory. It actually says everything. So if I have a carbon surrounded by 4 hydrogens, we have a CH4 molecule, and we tried to use the p orbitals to make the bonds, we'd have some of the hydrogens at 90 degrees to each other. That's too close. We can do better if we spread things out better. And the s orbital doesn't really have a direction, so you'd have a random H at a weird angle to these p orbitals. So what we have to do when we're going from an atom to the same atom in a molecule is to hybridize these orbitals. And we have to hybridize the correct number of orbitals to get the number of things surrounding the atom separated by as far apart as we can possibly get. So hybridization accomplishes that for us. So there's only 3 hybridizations you're responsible for in organic chemistry. There's the hybridization that has to occur when you need to separate 4 sets of electrons. That was that example I told you. You got CH4. I need to get those 4 H's separated as far as possible. I'm going to hybridize all 4 of my orbitals, and I'm going to get 4 hybrid orbitals called, here's their name, Sp3. So what do you get when you use 4 atomic orbitals? You get 4 hybrid orbitals. What's the name of them? Well, it's the name is based on all of the names you use to get there, an S and 3 P's. And you have no more p orbitals left over because you used them all. And now you're going to overlap these hybrids with other orbitals from other atoms, and you're going to make sigma bonds. So hybridization is used to make sigma bonds, is what we know about hybridization so far. You got it? Okay. Now, what would happen if I had an atom surrounded by only 3 things? Well, we're separating 3 things, and we're going to need 3 orbitals to do that. We're going to pick the S always. Do you know why we pick the S always? The S is the closest to the nucleus. It's a little closer than the P's, even though they're the same valence level. Its shape means it's symmetrically closer to the nucleus. Just look down at the bottom of the page. You got the P is way up here. Is there anything way up there in an S? No. Okay, so if I need to separate 3 sets of electrons, I only have to use 3 atomic orbitals. 3 atomics give 3 hybrids. What's the name of them? They're sp2 hybrids. Okay, we have to account for the orbital we didn't use. We did not use the third p orbital. Doesn't mean it's not going to be used. It means it's going to be used for the other kind of bond. Remember, hybridization is to make sigma bonds. The other kind of bond is made with an unhybridized p orbital. Okay, so we're going to overlap the 3 hybrids and make 3 sigma bonds. The leftover p orbital is going to be used to make a pi. P makes pi. That's easy to remember. They start with the same letter. All right, now you sometimes only need to separate 2 sets of electrons. This would be our final hybridization. You're going to need to make 2 hybrid orbitals. We always use the s, and to get to 2, you only need 1 of the p's. So you're going to make 2 sp hybrids, and you're going to have 2 p orbitals left over, which means you can make 2 separate pi bonds. Okay? And 2 sigma orbitals will make sigma bonds, and the p will make pi. All right. So let's look over on our next page. Here's a pictorial representation of what we just talked about. Here's the shapes of the orbitals, the s and the 3 p's. You mix them together by the process of hybridization. It's what the atom does to move things away from each other. You get hybrids that look a little like an S. They're round, but they still have the 2 dumbbells like the P. So that makes sense. A hybrid is a blend of 2 things. Just like you're a hybrid of the genes of your 2 parents, and you look a little like both parents sometimes. Okay, so we got 4 hybrids, and each can hold 2 electrons, and you can make 4 sigma bonds. Hybrid orbitals are used to make sigma bonds. If you forget that, it's down here. Hybrid orbitals are used to make sigma bonds. One thing I held back, they are also the location for lone pairs. You can put lone pairs in hybrids as well. So what's the other kind of bond made from? This is review. We already talked about it. The pi bonds are made from unhybridized p orbitals. Okay. So when we wanted to separate 3 sets of electrons, we're going to use the sp2 hybridization. Okay, an s with 2 of the p's, and you get 3 hybrids. The hybrids always look the same. Their angles change a little because you can separate 3 things better than 4. Better meaning bigger angles. But the hybrids themselves look the same, and you have the leftover p, which is going to be used to make pi. And similarly, if you only need to separate 2 sets of 2 groups of electrons, you're going to make sp hybrids from an s and 1 of the p's. Hybrids are here. They're pointing away from each other, and here's the unhybridized p orbital is going to be used to make pi. All right. I'm going to go and grab something else from the book right now. Hold on a sec. I got to do this in the right order, or else I'll mess up again. And I'm going to pause the video. And you can't see what I'm doing. It's okay. I'm not doing anything nefarious here. Grab one of these at a time. We'll look at the sp3 scenario first. Now, if we don't go to the shared screen soon, somebody's going to chime in. I'm looking for that. No, I'm not. I'm looking for this. Got it. Shared screen. We should be over here, but I don't think I started the recording. Stop. There. Start recording. So you should have my face here. I'm going to share now. And I'll give a few seconds. If you're not seeing Sp2 title inside of a box with these hybrids surrounding carbon, then I messed up. But I'm not hearing from anybody, so I'm going to move on. All right. So a lot of you are saying, what am I supposed to use this information for, right? What's this all about? Well, here is a molecule. I should be able to have a molecule like this drawn, and some of you already know what that means in this. They're really just 4 bonds. All 4 of these are just bonds. This one is trying to show you the H is coming out of the page. That's called a wedge. Wedge is a sigma bond coming out of the page. And this here is a dash. It's a sigma bond going behind the page. But hid. No, it's not hidden. Behind the page. No of. Okay, so the angles, it might not be obvious, but the angles are all the same. It's more than 90, which is better than the p orbitals we're able to provide, right? And this is more than 90, and this is more than 90. And it doesn't look like that's more than 90, but don't forget, that's coming out and that's going back. There's a lot of room in there because we have a 2-dimensional page, we don't see it. And the magic angle you have to learn for when you have Sp2 hybridization is 109.5 degrees, which some of you know already. Now, how do I know? Just by looking at this molecule. If I gave you this molecule, even if I drew it like this, if I drew this, I expect, this is not drawn with the proper geometry, but I still expect you to know it's Sp2 hybridized from the carbon's perspective. How do you know it's Sp2? Just if I started right here, it's quite easy. You count up the number of sigma bonds. If it's just one bond, it's called a sigma bond. And that's 1, and that's 2, and that's 3, and that's 4. You put your hand up. You've got 4 fingers up. S, P, P, P. The name of the hybrids are Sp2, and there are 1, 2, 3, 4 of them. Not bad. Okay. Now, I'm going to try to tell you why this oxygen here is also Sp2. You got to remember this big, bold sentence at the bottom over here. Hybrid orbitals are used to make sigma bonds or to put lone pairs in. So to determine the hybridization, I'm going to write that down. To determine the hybridization, count the number of sigma bonds an atom has and add the number of lone pairs. Don't worry, I'll be moving the comment. I want to make it big and give it some nice color and then move it for you. Make it bold. Okay. It's AHS. Dyslexia, huh? Oh, I can't do that. That's sad. It's a typo. Has. H-A-S. Hello?
Question.
Mm-hmm.
Hi, so I have a question. So for the sp hybridization, there's a sentence that says the hybrids are used to make S bonds. Is that just sigma, like the ones above?
So you found a typo in the book, maybe? Where in here or this page?
Yep.
I used to make S. Oh, you found a typo that's been there for years. Yes, the
Oh,
sentences should always be the same. Make sigma, make sigma, make sigma. Yeah, congratulations. You get a star.
okay. Thank you.
So here we go. Cross it off here, and I can't. It's not letting me. Sigma. There we go. Okay, so going back to our thing here. I know time's short. We're probably going to finish with just this SP3. Count sigmas and lone pairs. Well, there's 0 lone pairs. How many sigmas? 1, 2, 3, 4. How many pi's? 0. Pi has and pi has nothing to do with hybridization. Remember, pi comes from unhybridized p orbitals. So you're only counting 2 things to do hybridization. It's sigma bonds and lone pairs. When the total's 4, your fingers tell you the name of the hybrids and how many there are. The name is SP3, SPPP is called SP3, and there's 4 of them. Nice. So you figure out over the weekend when we have SP2 and when we have SP, and I believe this is a good stopping point for us. And I will not be posting the links right away because it's getting dark and I have to go for my evening walk. Very important, get my head straight and my body. And so it'll be tonight. So you have to hang in there. And I will see you Monday. And have a great weekend. And let me make sure I do this properly. I will bid you adieu.